Okay, so last time we talked permutations and combinations, right? Factorial permutations, combinations, and I think that's kind of a lead-in to what we're going to talk about today. Although we're going to start off a bit more abstract, we're not going to. We're going to talk about a kind of general analytic approach, and we're going to approach this idea in three different ways. So, in this general analytic approach, we're going to have counting. We've done a lot of counting already, right? Statistical counting, or just counting in general, right? We've done quite a bit of that. And we've done a little bit of random sampling as well. And we're going to take also a closed formula approach. Now, these, just to be clear, these are three categories that are a little arbitrary. Like, I've defined these. I'm not taking this out of a textbook or something. We could boil this down to, there's just a very simplified way of approaching a problem. And we'll see. We'll look at each of these in turn and see how these relate to each other. How one might be more performant or less performant than another in a given situation, or when a problem is intractable in one, like a problem that's intractable from a counting approach, might be possible to, use a random sampling approach. So let's think about this idea of a general analytic approach. Okay, so we're gonna have three steps to this, and close that. In our analytic approach, we're gonna do three things. So I'll just say analytic approach. And these are going to be very general, right? So the first thing we're going to do is we are going to synthesize outcomes of some random process. Okay, so we're going to consider, in this analytic approach, we're going to consider a random process, or a stochastic or stochastic, depending on how you like to pronounce things. We're going to consider a stochastic process. Okay? And we're going to model or create a sample space, right? We've done a bit of that. And we're going to analyze. So, maybe more specifically, we're going to synthesize outcomes, right, of a function, of a phenomenon, of some data. We're going to observe or interpret values in that phenomenon. And then we're going to answer questions, right? We're going to ask and answer questions. Okay. So where we're going to start with this is analysis through counting. And like I said, we've already done quite a bit of this. And when I think about this, when I think about counting, I think of it as being exhaustive, okay? You get everything in a counting approach. In general, let's say, you get everything. So it's exhaustive specifically for discrete outcomes, or we could say there's a bins approach for continuous outcomes. Either way, we are counting, right? And when we were counting before, let's say we have three symbols, let's say A, C, and F, just to pick three things, we can start counting FFF, FFC, FFA, right? And then we can roll the A over, right? And we've got FCF. And I'm not going to go through all of these, but FAF. And then, FAF, FAC, FAA. And then, of course, we're going to roll this A over again, right? And I could fill all those out, but I don't need to. I think we get the idea, right? Now, let's think about a counting example. So the first thing, let's say we've got a game, a tabletop game, and we have battles between different players, right? So we've got, this player versus, this player. And they're going to battle. And the first thing that we're going to do is roll a die. Okay, so let's say we have a 36-sided die. Okay. And then we're going to pull a card from a 52-card deck. And then we are going to flip a coin 3 times. Okay. So we've got a phenomenon here. This is our phenomenon. We haven't set any rules to it. We don't know how. We don't know how these two players are going to battle at this point, but we can describe the phenomenon. Okay, so let's put this into code. And we'll say, so we've got the possible rolls for a 36-sided die, which is going to be the range from 1 to 36, right? So that gives us one component of the phenomenon. It gets us this component, the 36-sided die. Okay, so now let's figure out our, pulling a card from a standard deck of cards. So we've got 4 suits, got spades, we've got clubs, we've got diamonds, and we've got hearts. And then we have card numbers as well. So card nums, we've got 2, 3, 4, 5, right? And I'll just fill these in. So 5, 6, 7, 8. Probably would have been easier for me to use actual numbers and not, well, whatever. It's too late now. 9, 10, Jack, Queen, King, and Ace. Okay. So I'm going to, populate, it was easy enough to set up the 1 to 36 dice rolls. But these suits and cards, I'm going to fill in a, I'm going to make a list of cards, right? So I'll say for each suit in suits, for each card in the card numbers, we can say cards.append the card of the suit. So I'm just creating a simple string interpolation here, and this will be like 2 of spades and 2 of clubs, 2 of diamonds, and so on. Okay, so we can just take a quick look at that. So I'll just print our cards. and make sure that that is working as expected. Okay. So Python, and we'll do Analytic Approach. And card nums is not defined. Card nums. Oh. Huh. Oh, I see what's going on. There's no assignment operator. Okay, there we go. Okay, and notice we get 8 of hearts, 9 of hearts, 10 of hearts, jack of hearts, so on. We've got all of our cards. That should be length 52. And I could verify that, but I'm pretty certain it is. Okay. All right. So the last part of this is flipping a coin 3 times. And we've kind of already seen this to some degree. So let's say coin flips, and for flip 1, I'll do tails and heads. And flip 2 and flip 3. We can build our coin flips. So this is going to be all possible coin flips for 3 flips. And we can put in a list that contains flip 1, flip 2, and flip 3. Okay. All right, so let's go back to this phenomenon. There are 3 things we're doing, right? We've got a 36-sided die. We're pulling 1 card out of 52 cards, and we're flipping a coin 3 times. Okay. So if we're going to build a sample space here, right, which is, this is the counting approach. We've made kind of a strange number system, but this is a counting approach. We're going to traverse this, and even though we don't need this to be sequential, 1, 2, and 3, we could do it in some other order. Let's assume it is sequential. First thing you do is roll the die, then you pull a card, then you flip the coin 3 times. We can treat these as loops pretty easily. And I'm going to do this, capital S is our sample space, right? Or that's a symbol that we've been using for to represent our sample space. I can say, first deal with the roll of the die. I can say for roll in rolls. Then I can deal with the card from the cards for card in cards. And then I can deal with the 3 coin flips. So for flips in coin flips. And I can just build this sample space, s.append, and I can paste in the roll, the card, and the flips. And now we can take a look at this. We can observe our sample space, okay? So for, I'll just say res for results. For result in S, let's print each result. And let's take a look at what this is, right? And, one question offhand might be, how many of these are there? There's quite a few, right? But we can see how this plays out. This is a form of counting, right? There might be this nested counting happening in here. These the tails, heads is counting within the larger set of counting, but this isn't that hard to build, right? And what we end up with is something that is exhaustive of the possible outcomes. Now, how many outcomes are there? Let's find out. Let's print the length of S. So let's look at the cardinality of that sample space. 14,976 outcomes. So that's kind of our step 1, right? This is our synthesizing of outcomes through counting, right? This is our, I'll just do this. I'll make a comment and say, this is synthesize outcomes by counting. And now let's move on to step 2. Step 2 is going to be, observing our outcomes. I'm sorry, we already did that. Let me just paste. Let me cut and copy that. This is just kind of the what we call the exploratory data analysis, the EDA. We just take a look at it, right? We try to get a sense of it. Now, we could get into it deeper. We could say, well, we could get into it deeper. We could try to give some kind of concrete, interpretation of what's going on here. But I'm going to go ahead and put that into step 3, where we answer questions. We interpret what we're seeing here, okay? And for this one, I actually have a breakout, and I'm gonna give you this code. So this code builds your sample space so that you have access to S. Go ahead and throw that in the Slack. I'm also going to put in this traversal of the sample space in case you want to reference it. And I'm going to give you a challenge. So let me grab this. I'm just going to grab the whole thing and put it here where you can see it. All right. So suppose that the 36-sided die represents the range of an attack. To hit an opponent, that opponent must be in range, okay? So, for example, a roll of 29 will potentially hit another player who is 29 or less spaces away, okay? Excuse me. The card represents the amount of damage that the attack will commit. In order to actually inflict damage, 2 of the 3 coin flips must be heads, okay? So what is the probability of hitting an opponent that is 18 spaces away? Okay. So I want you to write a code snippet that provides the probability and round it to 3 decimal places. So I'm going to put 5 minutes on the clock for this. And you have everything you need. You will have to traverse, right? You'll have to iterate over S and figure out how many of those results would indicate hitting an opponent that is 18 spaces away. All right, so I'm going to set 5 minutes and do your best on it. Of course, I'm going to walk through an answer after the timer runs out. Okay, go for it. Okay, so I'm going to just take us through a solution here to show how we can traverse a sample space, fairly simply, and discover, the subset and discover a probability from that subset. Okay, so I'm going to collect all the possible hits. Okay, and I'm going to say range to hit is 18, and we're looking to, if we want to hit something that's within or that's 18 spaces away, we need to have a range from, greater than or equal to 18, right? So we're going to traverse our outcomes. We're going to traverse each outcome in S, and we're just going to look at each one. And if that first part of the outcome sub 0, right, that's the die roll, which we can see up here for, we can see right here for roll in rolls. If that is greater than or equal to the range to hit, which is 18, then we have the potential to hit. And if the outcome sub 2, right, which is the 3 coin flips, those have to have at least 2 heads. So dot count of H is, well, what did I say here, actually? 2 of the 3 coin flips must be heads. So not greater than 2 heads, but equal to 2 heads. So if those 2 things are true, I can say hits.append the outcome. Now, this just takes us back to our cardinality of A over cardinality of S idea. And I can say the probability here is going to be the length of the hits divided by the length of S. And the prompt asks us to round this, so I will do that. I'll round it to 3 places. Okay. So I should probably print that out, I guess. So there's a 0.198 probability, right? Or basically a 19% chance that we're going to hit that other player, okay? If they are 18 spaces away. And you might imagine that if they are closer, right? Let's say they are 8 spaces away, this probability should be higher, right? And it is. So, you could take this a lot further. We could answer a whole bunch of other kinds of questions. But essentially what we get out of this is an exhaustive approach to a given probability. So we don't know what the underlying mathematical formula is here. We don't know. We don't have like what we would call a probability mass function. We don't have something that is going to, we don't have something that's just going to spit out an answer if we plug some numbers in. We are exhaustively counting all these possibilities and working with that. Okay, so that's a counting example, and maybe I'll do this. I'll just put a bunch of right. We're talking about 3 different types of analytic approach here, or subtypes, let's say. The next type we're going to talk about is a sampling approach. And there's an advantage to sampling approaches, okay? We can start trying to solve problems that are intractable by counting through a sampling approach. That's just a thing that we can potentially do. Okay. So, sorry, one moment. Okay, so let's think about this. Sorry. Let me look at this question. Would the probability be the same as the product of the individual probabilities of rolling the 36-sided die and tossing the coin 3 times? Like 1 over 36 multiplied by not exactly, if I understand your question correctly, because we're actually, like, if you think about what we're doing here, we've got, you know, some range of possibilities in consideration, and for one of the items, we're taking everything. Well, it wouldn't be so much like that. We're taking everything above a certain value. So the probability of all of this. Oh, you know what? We can think about it this way. We can essentially think about it this way, but there isn't an exact probability here, and I think I was misunderstanding your question, but I think what you actually mean, can we take the probability of, say, this is that less than or equal to the die roll, right? It's going to be that. Can we multiply that by, what was the next stage of that? Or, you know, the probability of some card. But that's going to be, you know, we aren't really worried about that. For this question, we're taking everything. So this is just going to be times 1. And then, you know, multiplied by, you know, some chunk of this distribution. Really, it's going to be, you know, what is it, to something like, yeah, we can just multiply those independently. We can multiply these independently. We could figure this out in a different way. The way I'm doing it, I'm just traversing everything and making a Boolean, but we could just traverse one of those elements and, you know, look at that out of the subset, right? So, you know, if this is like 0.63 and this is 1 and this is, I don't know, 0.59 or something, right? We could just multiply those together. Yeah, definitely. Yeah, and that's just multiplication rule is what that comes down to. Okay. So, yeah, definitely. So that's the counting approach. So let's jump back to this idea of sampling. And maybe I'll... See, I really love sampling approaches. I think they're great for approaching a solution, right? So if we have some distribution and, you know, we're talking about parameters of that distribution, the probability, let's say even the specific probability of a certain outcome, but we don't have the means to really count all the outcomes, then maybe what we do is we set up a way to pull enough random samples out of this until we have some subset of samples, and we look at the probability of this sample set. And, you know, we look at probabilities in terms of this sample set. And when we do that, we can approach solving some pretty complex problems that we couldn't approach through counting. And I think that's kind of nice. So let's use. I have an example problem here, and we'll kind of walk through it. So let's consider invitations sent for a party. 20 invitations are sent out. Each guest can possibly bring up to 10 guests, with equal probability of between not going and up to 10 guests. No matter what, at least one person, you, will be at the party. this may be a little bit confusing, and that's okay. We can take a sampling approach to start figuring this out, and that's really the point here. So the first thing we do is we synthesize outcomes. Right, same thing that we did for counting, except we do it differently this time. I'm going to import choice. I'm going to say from random import choice, and I'm just going to write a function, I guess, called num attendees. And every time I call num attendees, I'm going to get a number back, showing a possible outcome. So we know no matter what, there's going to be at least one person at the party. So we'll start the number of people at 1. Okay. And the one person, you, are going to invite 20 people, right? So 20 invitations are sent out. So I'm going to say for whatever in range 20. And the reason I say whatever, if I haven't said this before, is that this is a disposable variable. We don't need it. We don't need 0 through 19 in this at all. So we're just going to say for whatever in range 20. The number of people is going to be a choice out of the range from 0 to 11. This is a little bit weird, right? So with equal probability between not going and each guest can possibly bring up to 10 guests. So that potentially can be 11 people. So this is the choice out of the range from nobody to 11 people. I'm putting +1 because we want to be inclusive of 11. Okay, so this actually gives us a sample, right? We can return the number of people, and that should be sufficient. Okay. So, we have this kind of funny story here about, well, you try to invite 20 people, how many people show up? Well, you never know. Maybe it'll be like 20, 30 people. I don't know. And then you run this model, analytic approach, and notice, 109. Well, is 109 indicative of how many people we'll probably get? Well, we don't know. Let's run it again. 137. Oh, okay. 122, 102, 115, 99, 111. So if you thought you might get 30, 40 people at this party, it's starting to look likely that you're going to get a lot more than that. And so we have a model of the phenomenon here. Now, what we're going to do with it next is kind of break it down into, we're going to observe or interpret these values. And the way that we're going to do that in a sampling approach, in fact, in any of these approaches, in general, what we're going to do is we're going to pack things into dictionaries. So let's observe the values that we get here. And to do this, I am again going to build an outcomes of some sort, right? This time I'm not using a list, I'm going to use a dictionary. And I am going to sample a whole bunch of times. I'm going to say, let's sample 100,000 times from this phenomenon of sending out invitations and seeing what happens. And we'll say attending is going to be the number of attendees for each sample that we take. Okay. If attending is not already in outcomes, outcomes sub attending will be initialized to 0, and in every case, if we have a specific attendant count, we're going to increment it by 1, right? So this little snippet of code is really important, and so let's kind of think about this for a second. We build a dictionary, right? We have this outcomes dictionary, and we sample and we get a number, we get a scalar value, right? We get an integer that says this is how many people are attended in this experiment. And we check to see if we already have a record of that count of people attending in our outcomes. And if we don't, then we add that to, we put attending in there, right? We put that number in there. So if this is 109, suddenly outcomes sub 109 is going to have the value 0. And then we immediately increment that 0 to a 1. So that's all we need to do to start observing these outcomes. Now, let's print this to terminal. I'm going to say for key and value in the sorted, I have to sort it, okay? Well, let's run this without sorting it first. So for key and value in the outcomes, and I have to do dot items here because we're unpacking the key and the value. I'm going to print the key and the value. Oops, value. Okay. And let's see what we get. All right. So here are, in no particular order, all the potential outcomes. Now that isn't all that helpful, is it? Like, probably what we want to do is sort this, because in the random sampling approach, we're not going to get the lowest value first. We're not going to get the highest value first. We're going to get some other value, right? And if I sort this, at least we can look at it in order. Okay. I think I'm still printing something up here. Yeah, I am. Get rid of that. Okay. So now we can get an idea of this distribution. So in this sampling process, we didn't get any count lower than 48. So it kind of looks like 48 might be a minimum. If I run this again, maybe we'll get 47 or 46 or 43 or 61 is the minimum. We don't know this yet. So when I count through these, 48, 49, 50, 51, 52, 53, these are all pretty low, right? And then we start gaining much higher values as we get around, well, let's see, somewhere right around 112, it looks like. That might be our highest value here. If I run this again, 112 might not be our highest value. And why don't I just run this again and see? And when I look at 112 now, it's actually 111 now that has the highest value. Okay, well, at any rate, we're seeing some kind of modal, some kind of expectation that's sitting right around 111, 112. I could run this over and over again, and that would possibly get us to, and we could run it over and over again, average the results, and possibly see something more indicative of the theoretical distribution. And I want to point out that we don't have, something we don't have here, we don't have a closed formula, again. So in the counting approach, you often do that because you don't have a closed formula. In the sampling approach, you often do that because you don't have a closed formula. Also, it's intractable to count, or potentially intractable to count, right? So using sampling, you can get to something that is akin to the theoretical distribution, although it won't be the theoretical distribution. Okay. So let me give you this code up to here. And I'm going to challenge you to do another part 3 here. And again, part 3 for us in this is answering questions. So we have the data, we've synthesized the data essentially, and we can use that data to answer questions. Okay. So given a sample of outcomes, provide code to deliver an estimated probability that between 80 and 90 people will attend the party, and round that result to 3 decimal places. Okay, so I'm going to put I'll put 5 minutes on this, and see if you can figure that out. Okay, so these kinds of questions may not seem immediately obvious, but I definitely suggest going back through them on your own and figuring them out, picking them apart. So in this question, given a sample of outcomes, provide code that we're going to get between 80 and 90 people to attend the party. Okay, so I'm just going to call this 80 to 90. And this is going to be a counter in this case. And we have a total number, right? So this is the sum of the outcomes dot values. And we will go from there. Okay. All right, so for attendees in range 80 to 90 plus 1, this is how I'm going to do this. 80 to 90 80 to 90 is going to get incremented by the amount of attendees, okay? Now, I hope that makes sense. So we're starting at 80, and we're looking at the count, the value associated with outcomes.80, and maybe that's, I don't know, 3,000, not 3,000, like 1,000 something, and we throw that into 80 to 90, and then all we have to do is print our subspace, right? We need to print, let's say, 80 to 90 divided by the total, okay? And I'm going to round this again. I'm going to round it to 3 places. Oh, I probably need a close curly brace. Yep. Okay. So let's see. Let's see what this is. Looks like 80 to 90 people is something like 7.1%. Now, if I run this again, 7.2, well, it's staying pretty stable, right? 7.2 again, 7.3, right? So we can figure out these subsets. We can work with them. And so this sampling approach helps us to answer a question that maybe none of us really intended on answering at any point in time, but it does help us to approach solving a problem that we wouldn't otherwise know how to solve. I'm going to comment that out because it takes a little bit longer to run. And then I'll also comment these out. Okay. All right, so that's a good moment. Let's take a 6-minute break. And when we come back, we'll talk about the closed formula approach, which is kind of the friendliest and simplest to put into place of these 3 approaches. And yeah, we'll sort of tackle a simple problem with it. All right, I'll see you back here in 6 minutes. Okay, so let's get back into it. So we've talked about a counting approach, and we've talked about a sampling approach. The other approach that we're going to consider here is what I'm calling a closed formula approach. And that's not to say that these aren't, again, these are not definitive names of these things. These are just different approaches to generically solving problems, okay? So let's think about this in terms of a prompt. And the prompt we'll use is a little bit flawed, but that's good, I think. I think we'll be able to notice the flaw shortly. Okay. So consider a collection of spherical containers used to hold super gumballs that have a radius of 1 inch. These containers range from 4 inches in radius up to 100 inches in radius. Okay. So we're going to consider a rough count of gumballs per sphere. And we have a formula here for spherical volume, 4/3 pi r cubed. So again, we've got 3 general steps, and those steps aren't going to change. The first thing we're going to do is we are going to synthesize outcomes, right? What does that mean in this case? Well, for us in this case, it just means writing this formula in Python code. So I'm going to say from math, import pi, because we'll need pi. And I'm going to define a simple function called spherical volume. And we're going to pass in a radius, which I'm naming r. We can just return 4/3 times pi times r cubed. Okay, that's really it. Let's print the spherical volume of an object that has a radius of 5 whatever units we're talking about. We're talking about inches. So the spherical volume of, let's say, a container that has a 5-inch radius. So it looks like that's 523 inches cubed. Okay. So we've done that. Let's move to step 2, where we are going to observe results, right? Observe values. Now, this is going to be a little tricky, okay? What are we observing in terms of values? Well, I think what we're really trying to consider here is the capacity of a range of gumball containers, right? So that's where I'm going to start. I'm going to code something to demonstrate the capacity for, how many gumballs will roughly fit into a certain radius container. So I'm going to call this gumball capacity. And what I'm going to do here, I'm going to pack in a dictionary. I think that's a nice way to view this. So first thing, I'm going to define a dictionary as D, and then for each radius in range, and let's say that the containers range from 4 inches to 100 inches, so we can say range 4 to 100 plus 1. Okay, so this is nice in a way because we have a formula, we've implemented it in code, and we can just pack in these values. So let's say spherical volume so d sub r, each radius is going to be associated with a certain number of gumballs. Well, the spherical volume of a container is going to be r, just that radius. We're going to pass in the radius and get the spherical volume. And then we are going to see how many gumballs fit into that. Well, we can just divide this by the spherical volume of an object that has a radius 1. So that's going to give us, again, it's going to give us a rough estimate. And think about why it's a rough estimate in this approach. If it occurs to you why this is a rough estimate, put it in the Slack. Say something about that in the Slack. Why is this a rough estimate in this approach? At any rate, we can look at this. We can look at each radius and value associated out of this dictionary that we've constructed, and I'm just going to call the function directly gumball capacity dot items, and we can print the radius and the value associated with that radius. Yeah, it doesn't consider the gaps between the gumballs. That's why it's rough. And we might be overestimating the number of gumballs that fit into any one of these things. And we might be overestimating by a little bit. But we're not going to worry too much about that. If we want to make this function better, we can. And, we would have to find a good approach to calculating that. Those problems are pretty fun. Feel free to try to solve that problem better than this. But this is good enough for what we're doing right here. And I think it also shows that even though we're using a closed formula approach, it doesn't mean we're getting a definitive answer. Okay. So here are, is there something? Huh. Let me just double check something. 4/3 pi r cubed. Okay, yeah. Apparently we can hold quite a lot of gumballs in any one of these. Oh, I want to cast this to an integer, by the way. Okay. Run that again. So apparently we can hold 1 million gumballs in... Wow, that doesn't seem correct to me. No? I guess that is correct. Those numbers just look really big to me in terms of how many gumballs we can actually store. So one thing that we do notice here, and we can start describing this phenomenon through this, as the radius grows, the number of gumballs that we can store increases just dramatically, right? Really, really increases. And so that's something that we want to be cognizant of. That is a description of this set of possibilities in relation to the containers and the gumballs that we can see them store. Okay. So what I'm going to do is I'm going to write a function, and this is a little bit different than the last two, but these approaches are not set in stone. Like there's some different kinds of questions you might start trying to answer, right? So this is going to be one of those questions. So answering questions. What size sphere will it take to accommodate n gumballs? Okay. So let's think about that. All right, so I'm going to say get sphere, and let's say we have a certain number of gumballs on hand, and we want to know what size sphere we can use to accommodate those. So the first thing I'm going to get is this dictionary called gumball capacity, and I'm going to say for kv in d.items, if that value is greater than the gumball inventory, then we should be able to return that value of k, right? Pretty simple. Oh, we don't want to return d. If we don't find a size of container that will accommodate what we have, then let's just return no appropriate size. Okay. So let's say we have 10,000 gumballs, and we want to put them all into one container. What size radius do we need? Let's find out. We need a radius of 22 at least to accommodate that. More likely, it's going to be a little bit larger than 22, right? Because we've got these air gaps, and the air gaps we are not accounting for. But this gets us within striking distance. Okay, so basically, let's just sort of scan back over this a little bit. These are all these are all analytic approaches. These three approaches are analytic approaches, but they look pretty dramatically different, right? We've got a counting approach where we exhaustively, build a sample space, and we look for the cardinality of something over, cardinality of a subspace over the sample space. The sampling approach is not that different from that, except we have some kind of randomness, and we are modeling the phenomenon, instead of mapping out every possible outcome for some dice rolls, we're just rolling some dice. And we can see that allows us to answer fairly complex questions, right? Such as this one where we made a description of invitations to a party, and were able to, fairly clearly answer the probability of getting a certain range of attendees. And then we have this closed formula approach, and this is easy, right? This is just, we have a math formula. That's easy. And we populate a dictionary with those outcomes, and then we try to answer a question. And the question in this case is let's generally solve this idea of how many, what radius container you need to accommodate a certain number of gumballs. So those are going to be our three approaches in the general analytic approaches: counting, sampling, and a closed formula approach, if we have a closed formula to work with. So we're going to jump into something a little bit more theoretical for a bit here. And this is going to inform the next couple lectures, okay? So what we've got coming up, what we're talking about today is general analytic approach and discrete random variables. But what we're going to be talking about starting tomorrow and for the lectures after that is going to be the discrete distributions that we cover. We don't cover all discrete distributions, just to be clear. We cover a couple of them. And we cover them because they are indicative of, other distributions. We're trying to build a relationship with statistical concepts, and you can look up all kinds of distributions and play around with them and learn them. We're just going to focus on a couple of them because they're particularly common and particularly important for other algorithms. Okay. So we're going to start getting into discrete random variables. Okay, so discrete random variables. And that kind of brings up, well, what is discrete? Now, we talked very briefly about, well, no, I don't think we did actually yet. I'm probably gonna cover this particular concept a few times. I'm gonna talk about something being discrete versus continuous. And I think it's a fairly straightforward idea. I think we did talk about this once, but I'm going to talk about it at least one more time after today. So let's think about discrete. Let's say we have a range of numbers from 0 to 10, and we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So if we're thinking about this range of values, and we make a rule, we say, okay, well, anything in this range is going to be, we're just going to call it 1, and then this will be 2, this will be 3, 4, and so on. And we decide there is nothing between 0 and 1. There's no 0.5, there's no 0.9999999, nothing like that. If we decide there's nothing in between those two, then we are essentially discretizing something. We're not allowing there to be anything in between. It's either going to be 0 or 1. There's not going to be a 0.5. And this idea of discrete lends itself really well to certain kinds of concepts, like counting, for instance. When you're counting out loud, you don't say, 1, 1.0000000000001, 1.00000000000, you discretize those seconds. If you're counting in seconds, you discretize them. And part of what that means, is when somebody asks you, well, how many seconds elapsed between this time and that time? Well, you don't give them a partial second. You tell them what you counted up to. So discrete things could be people. They could be, specific objects where we don't, make a fraction of those objects. We treat them as either there or not, right? Not partially there. So in contrast, we've got the concept of something being continuous. I like to think about continuity in terms of time. Currently, we think of time as being continuous. Maybe it's discrete if we had precise enough instruments, but it probably isn't. Seems like it's continuous. And so we have from 0 seconds up to 1 second. If we have a precise enough instrument, we could take this point at, say 0.1 and take that to 0.2 and build another number line, right? And maybe we could say 0.11 to 0.12, right? And we could keep doing this. We could keep subdividing these over and over again until we have, we narrow it down to a tiny, point in time that is infinitely precise. The idea here being that if we had a powerful enough tool for measurement, we would be able to perfectly measure something, and it would have infinite precision. It would have, 0.1111 forever, right? We don't have this kind of instrument. So we're never truly dealing with measuring anything continuously, or anything that is continuous. But we have sort of different ways of conceptualizing this, right? We can look infinitely into a moment in time, and keep going and keep going and keep going, and there will never be an exact moment, right? There's never a discrete moment at the bottom of all that. What we can do, though, and what we also do all the time, is we take continuous values and we make them discrete, right? So we divide minutes into seconds, let's say, but we don't divide minutes into nanoseconds, or even more precise than that. We don't do that because it's not convenient. So just because it's continuous doesn't mean we treat it in a continuous way. We often do discretize things. So that's just a quick word on continuous versus discrete. We are dealing with discrete random variables. Okay. So what do we mean by a random variable? We're going to call a random variable an RV. That's common. We say RV. So the way that we can think about a random variable is it is a representation of potential outcomes. Okay? So it represents potential outcomes. If we populate that random variable with some potential outcome, we can also ask what is the probability of that potential outcome. And that's going to be very helpful. So how do we think about this? Well, one of the things we're going to do is we are going to define a random variable. We might say let's say let the random, I'll call this RV, why not? Let a random variable x, okay? So I'm naming it. Let the random variable x represent the sum of ones, the count of ones, in a base 3 number of length 3. So what does that look like? Well, it's going to be 0, 0, 0, 0, 0, 1, 0, 0, 2, right? And all the way up to 2, 2, 2. Okay, well, I actually have a little output of this. Here are all the possible all the possible outcomes of the underlying phenomenon, okay? But remember, we defined our RVX to represent the count of ones in a base 3 number of length 3. These are base 3 numbers of length 3, but these are not the components of x. These are not the possible outcomes of x. X has to be a count of ones. It's not going to be 1, 0, 1. 1, 0, 1 we would count as 2, right? So I have, what that translates into here. And notice it's kind of a neat little pattern, right? We have some kind of nice symmetry here, given the underlying phenomenon. So these are the potential outcomes of x. And we can start thinking about answering questions. We can ask the question, what is the probability that x is 3? Okay? And that's how we would write that. Probability of x is 3. So what we do is we divide, we count the number of occurrences of 3. And we should be able to see offhand, there's only 1 in here. And we divide that by by the total number, right, which is 3 times, well, you can see right here, 3 times 9, so that is 27. So the probability of getting 3 as the result of, the probability that x would equal 3, that x is going to, upon a random draw from this, that x would be 3, is 1 out of 27. And we can see it very clearly here. One item in here out of the 27 items has a value of 3 according to the rule that we've set. So we can kind of stick with this same phenomenon. And maybe I'll set this aside for a second. We can define a different random variable. So let's define a different random variable. So let some RV equal y. So this is going to be the definition of y. Y represents whether a 2 is present in a base 3 number of length 3. So is there a 2? And we can look at this. We can kind of break this down and consider this. So this is a true or false, right? This is just a 1 or a 0. And we can kind of like scan through these, and I'm going to just cross out anything that doesn't have a 2, and we'll just assume that those are, well, let's see. And so this is a very different set of outcomes, and I have this in a binary form that I'll show. So we're dealing with something different, right? We're dealing with the same underlying phenomenon, but we have defined a different rule for this random variable. And we can answer a question such as, what is the probability of y equaling 1? Okay? And maybe the rule here is that if y does not contain, if the underlying phenomenon does not contain a 2, then it's a 0. If it does, it's a 1. So how many times does y equal 1? Well, it looks like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So that's 19 out of 27. Again, it's the same underlying phenomenon, but we've defined a different random variable. So those questions are, if we're asking the question, the probability that y equals 1, if we're asking that question, this is where we might apply something called a probability mass function. Probability mass function. And in general, we'll call these PMFs, okay? Probability mass function is a PMF. And this is related to discrete distributions. Continuous distributions do not have PMFs, they have PDFs. So what we're talking about here is a PMF, probability mass function. So what a PMF does is it describes the probability that an RV has a certain value, right? Again, the probability that the random variable y would equal 1. Or the probability that the random variable x would equal 3, right? So when we represent these, we often do this. We say the probability that big X is equal to little x, where this big X is what we think of as the random variable, right? Which is all potential possibilities, all potential outcomes. And this little x is a specific outcome. So the probability that big X is little x. And generally we'll describe these in that format. Okay, so that's a probability mass function. There is another kind of function that we can consider, and that is a CDF, or cumulative, I believe it's distribution function. I think I learned it as density function, but you know what? Let me just double check that against Wikipedia, because I think I always get a little hung up on this. It's cumulative distribution function. Yeah, when I was taught, when I learned about CDFs in school, my professor called them cumulative density functions. They are generally called cumulative distribution functions. And either way, we're going to say CDF for these. So we can think about the CDF as being a sum. It's the sum of all probabilities between, up to and including some value of x. Okay, and the way that we're going to see this is the probability that big X is less than or equal to little x, where big X represents the random variable, little x represents a specific outcome, or the highest potential outcome. So how can we describe the CDF a little more clearly? Let's think about heads and tails. Okay, so let's do tails, tails, tails. Tails, tails, heads. It's going to take me a second to write out. Tails, heads, tails. Tails, heads, heads. Heads, tails, tails. Heads, tails, heads. Heads, heads, tails. And heads, heads, heads. So that should be 2 to the third power. 1, 2, 3, 4, 5, 6, 7, 8. And there's 8 of them. And let's say we define a random variable z. Z represents the count of heads. How about that? That's easy. And so we can start breaking this down. There are 0 heads here. There's 1. There's 1. There's 2. There's 1. There's 2. There's 2. There's 3. And so we might ask a question. What is the probability that z is less than or equal to 2? And it might be obvious what this is. There's 8 outcomes, and there's only one outcome that is not less than or equal to 2. And we can see that this is 7/8. How do I do that? Well, I can look at the probability. If I want to really break this out, I can say, what is the probability that z is equal to 0? Add to that the probability that z is equal to 1, plus the probability that z is equal to 2. And that will get us the same result, okay? So z is equal to 0 is, 1/8. Z is equal to 1 is 1, 2, 3/8. Z is equal to 2 is 1, 2, 3/8. 3/8 plus 3/8 is 6/8 plus 1/8 is 7/8. So we can see that these two things are equivalent. So let's think about another example of this. Let's say we have the random variables. Let's not use z. Let's use a. So a represents a sum of ones. Well, you know what? I basically just did this example, but I did with 3-bit binary, not 4-bit binary. But as we can see, the CDF is just the accumulation of the PMF, right? So think about it that way. The CDF is the accumulation of the PMF starting at the lowest value in the distribution, or the lowest value in consideration, to some value of interest. When you're writing a CDF, it's really nice to have the PMF. Okay. So this kind of leads us into our discrete distributions. And so we're going to go a little bit ahead today into the next lecture. So the first distributions that we're going to think about in our discrete distributions are going to be Bernoulli and binomial. These are directly related. Often we'll call binomial a Bernoulli process, or we'll call it a binomial process, or we'll call something the binomial distribution. The way to think about these, well, we've been kind of working with these already, and we haven't been very clear about working with these yet. But Bernoulli is like a coin flip. There are two outcomes, and there's a probability of success on any given outcome. For a coin, that would be a probability of 0.5, right? If you have an unfair coin, I don't know, maybe it's a probability of 0.7 that you're going to get heads. So that is essentially Bernoulli. You have some phenomenon that's sort of like a coin flip. So it can only be one of two things, failure or success, and there's a probability of that success. Binomial is a series of Bernoulli trials. We have a fixed P. We have a fixed probability. So I'll just say fixed probability P. And we've kind of been doing binomials, and maybe you didn't realize it because I never said. But if we are looking at, tails, 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 heads, tails, heads, tails, tails, heads, heads, etc. If we're looking at this and so on up to heads, 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 and we're asking a question regarding the number of successes in n trials, right, where in this case n equals 3, we are just counting the number of heads. We're just counting the number of heads that might occur in 3 coin flips. That's a binomial distribution, as it turns out. So the way that we want to think about these, if we have Bernoulli, what we might be asking is, what is the probability of success, given that you know the probability of success, right? Bernoulli is very easy. It's very straightforward. It's literally a coin flip. We're considering the probability. When we're talking about binomial, what we're essentially saying is, what we're asking is, what is the probability of k successes, right? What is the probability of k successes in n trials? And that may sound very straightforward, and it is. It's fairly straightforward. But if we're thinking about k successes in n trials, there are a lot of different arrangements that might lead to k successes, and this brings us back to combinations, actually. So, if you have, and let's think about these as coin flips, right? Where zeros represent tails and ones represent heads. If you have something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you have 12 coin flips and you're asking, well, what is the probability of 3 heads in 12 coin flips? There's a lot of different ways that we could arrange 3 heads in 12 coin flips. There's 2 ways right there. I'm not going to be exhaustive about this because I don't, oops, it's 4. I don't want to, I'm going to fill up this space over and over again. This implies combinations. And when we get to the binomial PMF, the closed formula for the binomial PMF, we'll see combinations inside of it. It's there clear as day, and it makes sense for it to be there. Okay. So that's just touching on the binomial and the Bernoulli trial, the concept of a Bernoulli trial and the binomial distribution. There's another distribution that I want you to consider. And when we call things random, often we are actually talking about something that looks like a uniform distribution. There's a lot of different kinds of random, and random, we can have a binomial random. We can have a normal random. We can have a bunch of different randoms. And randomness has to do with how we sample from a distribution. Uniform is really easy to understand. And it's what we generally think of when we use the word random. In fact, random.choice we can think of as pulling with equal probability from some kind of distribution. Here it's 0, 1, 2, 3. It's not going to favor any one of these outcomes. It's going to pull them with equal probability. And so if we sample this a whole bunch of times, we're going to see a uniform distribution. If we were to plot that, right, 0, 1, 2, 3, we're going to see something that looks fairly uniform. It looks even, right? Often we'll represent the distribution like so, even though in this discrete form, we've got 0, 1, 2, and 3. These all occur with equal probability. But the distribution just kind of visually looks square because every outcome has an equal probability. If we ask the question, if we want to think about this in terms of rolling a die, if we have a 32-sided die, the probability of a given outcome is going to be 1 over 32. Doesn't matter which outcome. A 1 is going to have the same probability as a 9, as a 29. And so the PMF is pretty straightforward. It's, the PMF is going to be 1 over 32 for any given outcome, which is kind of nice. The CDF might not be quite as obvious, but CDF is also pretty easy. If we're asking the question, what is the probability that some random variable that represents the roll of a 32-sided die, let's say, the probability that x is going to be less than some value of x, that's going to be the sum of 1 over 32 times x, as it turns out. So what does that mean? Well, we start at I equals 1, and we go up to k, which is the value of interest, and it's going to be I. So if we were to ask the question, what is the probability of rolling less than or equal to a 12, then that would be the sum of 132 times x sub I. Oh, is it even that? no, actually, I think we can just think about it like this, right? It's actually just going to be 1 over 32 plus 1 over 32 plus 1 over 32 plus 1 over 32 12 times, right? So that's pretty easy. That's just 12 out of 32. Simple. Uniform distributions are nice, and they pop up a lot. They're going to be, we think of it as like, oh, it's this incredibly common distribution. It sort of is. And we find it very helpful. Uniform numbers are very helpful to us in a lot of things. And, we couldn't perform these simple sampling processes that we've been doing. We wouldn't be able to perform those without some kind of uniform sampler. We've been seeing that pretty directly, I think. Okay. So let's think about a Bernoulli trial, a specific instance of Bernoulli trial. Let's say you have a bag. You have a bag, and there's 2 colors of ball in there. There's green balls, and there are red balls. And we've got 30 red, and we've got 70 green. If you reach into the bag thousands of times, and you average the counts of those balls that you pull out. So you reach in the bag, you pull a ball, and you put it back. Reach in, pull a ball, put it back. What do you think would be the probability of pulling a red ball in general? What do you think that would be? Any thoughts? Yeah, it's just 0.3. And this is kind of what I'm getting at. Bernoulli trials are very simple, and they end up being building blocks for a lot of other things. Sorry, I didn't see this question come in before. Is this the same as a confidence interval? I believe, what was that in reference to exactly? Seemed like that was in reference to kind of constructing a CDF. I mean, we use CDFs in confidence intervals. But I guess I don't think about it that way. Yeah, I don't think about it that way. I'll have to think about that a little bit more, and see if I can tie those two ideas like concretely together, and I'll be happy to answer that after I think about it a little bit. So let's commit some code. I'm going to commit some code for a Bernoulli function, and that means that we're going to get into discrete distributions, and I've got this subfolder. No, I don't have a subfolder, but that's fine. So let's do code, and we'll look at Bernoulli. Okay, so I'm going to code a Bernoulli function. And the way that I'm going to do that is I'm going to say from random, import random. So notice, let's look at what random does first. So the random function is pretty straightforward. Python Bernoulli. We get a random number between 0 and 1. That's all random does. Turns out this is a this is a uniform distribution. This is a uniformly distributed value. Wow, that seems unlikely. I just got 7, 9, 7, 7, and 7, 7 in a row. But regardless, we will expect this to be any value between 0 and 1. Although, well, you know what? Randomness is globby, and if I run this enough times, I think we'll see that it is random enough. Okay. So what my function is going to do, not random exactly, but I'm going to define a function called Bernoulli. And what Bernoulli is going to do is, given a probability of success, it's going to return whether or not a trial was successful. And we're going to do that very simply. I'm going to take a draw from random. And this is going to get a value between 0 and 1. And, let's think about this like a coin flip. I'll set the probability of success at 0.5. And I'll say if the draw is less than the probability of success, then we return true. And otherwise, we return false. So that's a very simple bit of code. I think it's actually kind of powerful though, right? It's like, okay, we're going to take a random draw, and if the draw is less than our probability of success, we return true, otherwise return false. We could return 1 or 0, but those are going to be effectively the same thing for our purposes here. So let's verify this in some way. I'm going to sample from Bernoulli some number of times. Okay, so I'm gonna sample a whole bunch of times, and that many times. How many times is that? 10 million samples. That's what I'm gonna do, and I'm gonna say for I'm gonna do this in a very simple way. I'm going to call out to Bernoulli, okay, with the probability of success set at 0.5. And I'm going to do this 10 million times. So you may not have seen these very much. This is a comprehension. This just is going to help me not have to, it's going to be a little bit faster. It's going to be a little bit more performant. But all this is going to do is give me a bunch of Booleans, a bunch of trues and falses. And all I have to do here is count the number of trues. So count the trues divided by the number of trials. Again, this is our cardinality of A over cardinality of S. Same thing. And at the end of all that, I think, let's see, we should, the assumption here is that given the probability of success on every trial as being 0.5, we should average out to something like 0.5. It's going to take a little bit to run. And notice we get 0.50000 or 0.00443. And that's nice. That is showing us that this actually works. Now, I'm going to comment that out, and I'm going to write this in a longhand, and then we'll end it there. This is doing the same exact thing as if we want to break this out into a for loop. I can take a count of the trues started at 0, and I can say for whatever in range that number of trials, if Bernoulli of, where the probability of success is equal to 0.5, if that's true, we can increment our true count by 1. And then we can print the true count divided by the number of trials, and we should see something very similar. It should average out to right around 0.5. 0.49986, yeah, it's doing fine. So, this is a scheme to get a success or failure from a given Bernoulli trial. Notice we are sampling, and here we are seeing verification that that is working the way we might expect it to. Okay, so we'll start in on the binomial distribution next class. And, the way to remember this, Bernoulli trial is like a coin flip. Binomial distribution is like a series of Bernoulli trials with a fixed probability. Or binomial distribution is where you're considering the count of heads in a series of coin flips, n coin flips. Let's leave it there, and we're going to dig pretty. We're going to approach binomial as sort of like our model distribution, and we're going to figure out. We're going to figure things out from that. There's going to be a lot of things we figure out from that. So I'll go ahead and stop.